How's it going, everyone? Welcome, Elvira Gonzalez again. So, what I do want to do in this series of videos is ask a simple question, right? And that is, how do Ruby or interpreted language store objects in memory? So I went to this rabbit hole because a company hired me and say, hey, we need assistance here with this Ruby project, right? So they have a particular products where they want to promote certain content across social medias. So that's interesting, and most of the time, what you are going to do if you're working for any company, they're gonna hire you as long as you pass now that test, which I did. In the case of JavaScript and Node.js and TypeScript, but they say, hey, we need you to help us here with this Ruby project. I don't know how Ruby works. I went through this 20 minutes of Ruby docs to actually kind of sense of what Ruby is, which is an interpreted language, pretty much like, for example, Python and JavaScript, right? So far so good. The only thing that changed is perhaps the syntax and some of the internal API that it exposed, and also how now you execute programs here. So because of that, and since I truly don't know how, for example, Ruby store objects, and when I explore, for example, the RB, which is the read event print loop, as after I create objects or classes, right? So they give me is this memory address where this object belongs to. So I wonder, okay, that's good. So the in this case, the interpreted language somehow it take my set of instructions as an input, and then it pass that to the compiler, where the interpreter, where this generates some bytecode, and then using now virtual machines to finally generate the code that is going to be mounted in memory, and the CPU will execute that for me. But again, this doesn't solve the problem of how memory, or particularly how objects are stored in memory. And that was interesting because there is this particular course, right? boot.dev, where they have, for example, is the backend and developer path, right? Go from Python fundamentals to real backend system with Go, SQL, Docker, and portfolio projects, right? But what I do want to explore is more about how this memory management works. I do it by myself, the SQL things, or by actually reading at the standard, right? And as I reading this, right? So packed with 15 cores and 8 projects, this path takes most beginner about 12 months to complete. But in my case, it's say, okay, since I'm not gonna learn Python, right? Because most of the time, that's not the main language where I'm working on. This might be quite interesting in order to understand now Linux, but not right now. Build a bookbot, which is a particular project on how to do that. I'm assuming that they're using Python, as you can see the icon here. The other is this distributed version control system. So I am well aware of what Git is doing behind the scenes. The other is learn object-oriented programming here with Python. And again, another project, learn functional programming, build an AI agent, all right? And learn data structures and algorithms here, which is quite interesting. For example, algorithm, math, big O notation, sorting algorithm, exponential time, all of it, you know, stack, queues, linked list, binary tree, red-black trees, hash map, try, graph, breadth first search, and deep first, search P and MP, right? Is this computable, this problem or not? Build static site generators, again with Python, right? And then finally is this thing, which is the learn memory management, right? So that's where I'm going to do in today's video. This will be like 4 or 8 videos that I'm gonna record from this moment and on. So perhaps it might take me like 2 days. All right. So yeah, I'm assuming that each video takes me like two chapters, right? They say 1, and if this is 12, so if you divide that by 2, it gives you now 6. So allegedly, right, it will take me like 6 videos to complete this. If I'm taking that as I mentioned here, so 1 video per 2 chapters. All right, let's get into this. There you go. So this is the author, T.J. de Vries. I think that there is Deutsch, correct? TV's aka TG has never worked at Netflix, but if you have heard of Neovin, well, he's the maintainer. It is really not a big deal. And put the dev team contributor. So the point of this is not only to take his word as granted, but also look at the documentation, because at the end of the day, you can solve a lot of your issues by reading and understanding where all of this comes from. So, there you got it. Yeah, see, basics, right? And let's take a look at this starter course. But I also do want to do that with the help of what he described here. Or in other words, is based on his particular YouTube series, which is this one, right? Exactly. So he took for him 4 hours, or 5 hours to record this, which is holy moly. And that's exactly what I'm gonna do. Let me see if he actually mentioned is the book. No, he didn't mention the book. So I'll make a quick pause to kind of look at where I can find the book, at least the most recent, free, available, without copyright strike link, right? So I'll be right back. Okay, that was fast. So here it is, the clanguage.org, the lingua franca of programming. You got it. I'll be right back. All right, so this is the C programming, right? So C is a general purpose high-level programming language suitable for low-level programming. In other words, a system programming language. It stands out in terms of portability, interoperability, efficiency, and stability. First, I didn't know that this was part of a standard. It makes sense to be part of a standard. And it started in the 1978. Holy moly, bro. Holy moly. Right? The C programming with key and air as it is. You can take a look at the book sources. But yeah, and then it becomes now this another standard in December 1989. Almost 2 years later, okay, or 2 years later, it became part of the standard. As interesting, ISO, ISC, those stand for the International Standard Organizations and the Institute of Electrotechnical Commit, which oversees anything related to electromechanical conventions and standards, right? This was founded by Sir Sir Kelvin in Britain, in UK, right? So, but the point here is that they have released several of this, and it's interesting because, as you can see here, the first letter is start with the C programming, and then the other is followed by the year. That makes a ton of sense to say, hey, which version are you currently using? So if I go here to the About page, C was designed by Dennis Ritchie. All hail to Dennis Ritchie. During the early 1970s at Bell Labs, as an improvement upon the B language, created by Ken Thompson. For those who are not who is Ken Thompson, well, here it is. Right? He is still alive. Holy moly, sir. And he has come to several events. One of them is here in Argentina, Nerdearla, right? It's the nerding stuff, so stuff like that. So I won't pull this up here right now. I do think that's quite interesting. So this is Ken Thompson, right? Right? So Ken Thompson, right? Creating a language bee, and then he's say, hey, what you're doing sounds interesting. Back in 1978, 1970s, sorry. And after the release of the Unix operating system, this basics program that is going to run to manage your resource, hardware resource, and later also the publication of the first edition of the bestseller, The C Programming Language, authored by Brian Kenigan, together with Ritchie. So that's why they call his Kernighan and Ritchie, right? Which is the first edition in as you can see here, in 1978. Yeah, yesterday. C became one of the most widely used programming languages in the world. Let me see if
there's a book just over your shoulder that's carefully been placed there. Can you pick the book up and tell me about it? Or?
Right, great book. You should buy the newer version of this. Sorry, brief commercial announcement. Yeah, sure. I think I mentioned at some point in our conversation the fact that the people working on Multics, well, Multics was sort of the second version of time sharing that was done at MIT with collaboration of Bell Labs.
Collaboration at
and General Electric. Very big success. People working on Multics, well, Multics was sort of the second version of time sharing that was done at MIT with collaboration of Bell Labs.
So the question is that, what is this time sharing, bro? Time sharing systems that he mentioned. Time sharing is a method of sharing computing resources among multiple users. There you got it. In computing, time sharing is the concurrent sharing of computing resources amongst many tasks of users by giving each task or user a small slice of processing time. Makes a ton of sense, because at the end of the day, this concurring is things that can happen that overlaps at a time. So if, for example, if you are now making a meal, and then you suddenly your phone rang, or your phone rings, so you want somehow is to pause whatever you're doing in the kitchen, answer the phone. You say, oh, it's my mom. So let me is in fact sorry about that. Okay, so let me is in fact so pause whatever I was doing, answer my mom. Hey mom, I love you. I'll call you back. I'm in the middle of something. I'm boiling a pasta, right? So, or you can say, while I'm answering your mom, Then now I go back to the previous process that I was, which is preparing my meal. So this is what time sharing is all about. Hey, I want to use this resource, and the computer somehow, or the system somehow, can allow me to do that for me. So this quick switch between tasks, and I want to emphasize this, switch between tasks of users gives the illusion of simultaneous execution. It enables multitasking, truly multitasking, by a single user, or enables multiple users' session. So developed during the 1960s, it is emergence as the prominent model of computing in the 1970s, present a major technology shift in the history of computing. By allowing many users to interact concurrently with a single computer, time sharing dramatically lower the cost of providing computing capability. So not only that you have some particular task that you want to do, for example, is calculating is the amount of calorie that a particular nutritional diet in the next 3 months will took, and also you want to create another process to say, hey, how much money will it cost me? What will be is the amount of food that I need to buy, and so on and so forth, right? So all of this process is to answer particular questions. So that's what it is, right? So by allowing many users to interact concurrently with a single computer, time sharing dramatically lowered the cost of providing computing capability, made it possible for individuals and organizations to use computer without owning one. This notion is something that Amazon has popularized. All of these cloud vendor providers has popularized. Yes, having, and I think this is something that they want to promote in the case of AI, right? They want to say, hey, let's go to time sharing this resource so you can now have access to this. Just to make a quick pause here, I do think that the ownership is something that is important from the economic side. So from the economy and for your business operations, because if you see yourself as a business owner, right, somebody that is a service provider and need to keep up the pace with all of the things that happen in your business domain and your industry, and also you want to offer and to be palatable for your clients to say, hey, let's going to continue to do business. So it makes a ton of sense for you to own that particular hardware to run your own business operations. Again, that comes into the realm of centralization and decentralization and the business aspect. I just want to mention that real quick. And promote interactivity, use of computer, and the developing of new applications. So you get this, right? Time sharing, and the Wisconsin 1978, the development, right? Time sharing business, right? Rapid as an example, time sharing in the United States. But this is the whole point of, I do think that the story will repeat itself because, for example, in the case of AI, it's gonna become so cheap, and also following the laws more, this is gonna become so cheap that you can not only own your own computer for your own daily business operations, but also for running your application and the client's applications as well. Yeah, that's something part of my reads here. So there you got it. Time sharing, right? So it's a mechanism the operating system rapidly switches between user tasks using CPU scheduling and multi-programming. Okay.
Labs and General Electric. Very big system for providing, in effect, a computing utility for programmers. Multics was actually being written in high-level languages. They started with PL1, which was not a good choice, and then they moved to BCPL, a language which was developed, in fact, by Martin Richards, Cambridge. The people doing that who were at Bell Labs, in particular Ken Thompson and Dennis Ritchie, had gotten used to the idea that you could write really interesting operating system kinds of software and tools that supported it in high-level languages. You weren't writing assembly language. And
Okay. So again, remember, so there is no need to write, for example, is operating systems in assembly language, which is allow you to move one register to another. For those who are not familiar with assembly language, is a way to program your computer by moving registers and putting things inside of the registers that allow you to run is some operations. So for example, hey, I do want to now is do basic arithmetic. All right, so I have now several registers. You can think of this register as like buckets, right? Where you can put now is operands or values, right? Hey, I do want is to now calculate the something more. I would like to calculate is the discount that I'm going to make if I purchase my weekly food every Wednesday, all right, and receive a 50% discount. So I do want to know, well, how or what will be the total amount, or the total discount from that if I regularly schedule my food my weekly food purchase on every Wednesday. I know that it might sound, why in the French toast would I want to do that? Well, it turns out that here in Argentina, there is a lot of food or supermarkets that they have discount in Wednesday, because this is when now once they receive all of this food from different providers, so farmers, among other distributors, right? They receive that on Friday, so Thursday on Friday. So you have fresh food on the weekend, right? And then during the middle of the week, well, this food, of course, is gonna get bad. So they want to, well, incentivize people to actually take that at a discount, and that makes a ton of sense. So that's the reason why I mentioned that. So if you have that kind of questions, right? Well, it makes sense to say, all right, I do want to calculate to compute that. But here what they're saying is, because you have now this assembly language, and for example, you want to say, all right, so how much will it take, or how much, how much will it cost me to purchase all of these items, kiwis, bananas, guavas, sweet potatoes, blah, 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 you know? On that Wednesday, and well, each item has a price, so you put all of those prices in this register or in these buckets, right? And then once you have all of these prices here, you're gonna pass that to the computer, and the computer will give you the result at no time. So that's one of the main use case of going with assembly language. The thing here is that it is something that is not human readable unless you get familiar with that mechanics. So once you know how that things work, it'll quite becomes easy work. Right? But what he mentioned is that there is no need for writing a program, particularly a system operating system, to do that. So we can also have now is, well, this high-level program that looks like English, all right, that look like human, and we can now make sense of how these things will work if you share that with others.
So when they started working on Unix, this very small stripped down version that was done at Bell
Script versions, interesting.
languages, you weren't writing assembly language. And so when they started working on Unix, this very small stripped down version that was done at Bell Labs, they were at the same time exploring the use of high level languages. And there were a variety of these. There was a language called B, which was the first attempt. It was done by Ken Thompson, a very simple language, and I suppose you could say it was sort of like a stripped down version of BCPL. It's, kind of a weak naming convention there. And so you could do interesting things with B, but it wasn't quite powerful enough. And in particular, it was an interpreter, not a compiler. And that meant it didn't generate machine code for the particular machine it was running on. It was just a program that interpreted what it was trying to say. So it meant it ran relatively slowly. The other thing is that the language did not support the architecture of newer machines that were showing up, in particular the PDP-11. Newer machines, instead of having everything in the machine be a single size of, in effect, integer, let's say 16 bits or something like that, they had different sizes that the machine would efficiently and naturally manipulate, 8 bits, 16 bit, maybe 32 bits. And the language B didn't reflect that. And so Dennis Ritchie undertook to design what amounted to a version of B that was richer and had mechanisms in the language to say, this is an 8-bit quantity, this is a 16-bit quantity, basically the char and int types that you see in the early versions of C. And so he wrote a compiler for that, and then with the compiler in hand, they started to rewrite the operating system itself in C. And this took a while, but something in the order of 6 months.
Again, it's now, for manuscripted language, it creates now a compiler that it takes this C code source, right? And it generates now machine code per architecture, which means that I don't care how is the machine at the hardware level. When talking about these registers, I don't care is the size of this register or this bucket, right? It can be 8 bytes, 16 or 32, right? I don't care about that. What I do care is that I want to, whatever the architecture it is, generate code that is tailored for that architecture. Okay. So you can think of this like I want to generate code, or once I read the entire script, all right? For example, so what this architecture means, or what analogy can be, is because architecture can represent or can have internal representations of this data, right? 8 bits, 16 bits, 32 bits, right? It's like saying, hey, I know how to talk English, but I don't know how to talk Boomer English or Gen X English, not to mention Gen Z English. So this is like generations of sort of speaking code. So I don't care which generation that you want to talk. I want to create something that allow me to translate or to compile something that they can understand.
To get that working. And at that point, then you've got the operating system, and of course all kinds of other critical core software written in a high-level language rather than in assembly language. And that's important for all kinds of reasons. One, it means that it's just a lot easier for lots of people to see what the code does. You don't need so much expertise because it's in the high-level language. And the other thing is that it's portable in the sense that if somebody makes a C compiler for a different kind of machine, different architecture, then you can recompile whatever your program is for that new architecture, and in that way you can move your program to a different machine. Now this has always been the advantage of high-level languages, but now you could do it for the operating system. And that meant that Unix, the operating system, no longer was only PDP-11, but could run on a variety of other machines as well.
I think the concept of having a high-level language I get, right? You compile it down to hexes and machine code that tells the processes to do stuff.
Right.
And if you have a different compiler for a different machine,
that meant that Unix, the operating system, no longer was only PDP-11, but could run on a variety of other machines as well.
I think the concept of having a high-level language I get, right? You compile it down to hexes and machine code that tells the processes to do stuff.
Right.
And if you have a different compiler for a different machine, it just changes what those hex codes is.
Correct.
Right?
That's exactly right.
Exactly. So if you have now a compiler for different machines, that is going to change is the hex code that the machine can understand.
So it should be really simple to understand how you write an OS in a high-level language, but is it a bit like making a sharper tool and using that sharper tool to make a sharper tool?
Yeah, right. I think, in fact, and the complication is in writing an operating system in a high-level language and translating it into, let's say, multiple different architectures, is there's a lot of detail to get right there, and there are some things which the high-level language just doesn't support. So you need a little tiny bit of assembly language assist for any given operating system. The one that's more like the conceptual problem that you were explaining well is how does the compiler itself get started? Because of course the C compiler is written in C. And so there's the how do you get it started, and your idea of the sharper tool making yet a sharper tool and so on is metaphorically the right idea. Because what you do is you say, I wrote some code in C on paper. Let me mechanically translate that into something that will process a bit more of C code and then bootstrap myself up from that. So it's a bootstrapping process. And I've never done it, so take me with a grain of salt on that. But that's the basic idea.
Okay, so and then tell me about this book. How did this come about then?
So
I'm looking, I think that's a relatively early edition.
That's the first edition, yes.
Is it autographed?
This one isn't actually. Oh dear. This, however, is the 24th printing. So,
just point out Professor Phelps for just wanting a pen for the autograph there.
Okay, I will autograph it. How did the book come about? Somewhere early on in this process of people building interesting languages, I got intrigued by the idea of how do you explain those languages to other people, and so.
Hello. Oh my God.
I wrote tutorial documents. I wrote a tutorial document on B so that people could learn B, because Ken Thompson and, to a lesser degree, Dennis didn't write a tremendous amount of documentation, let's say. It was spare and there was not much tutorial stuff. So I wrote a tutorial document on B that was useful. When C came along, then I wrote a tutorial document on C. And at some point, I had already written, I guess, a couple of books at that point, and it seemed like that there might be a market for a C book. And so I twisted Dennis Ritchie's arm into writing the book with me. And that is the smartest thing I ever did in my whole life. No ambiguity. So we took my tutorial document as kind of a piece of it. We took his reference manual, which is a really excellent reference manual, as a big piece of it, took that verbatim, and then we filled in material in the middle to explain the various parts of the language at more length. And we published that, we wrote it in 1977, published it at the beginning of 78. And of course it was done with all of the document preparation tools that we had been working on over the years. And so it had mathematical expressions in it using EQN. It had tables of things like operators using Mike Lesk's TBL program. The first edition predates PIC, the picture a drawing language. But the second edition has pictures and so on. So is this incestuous, or is this building on what other people have done? I don't know, but that's how it came about. And I remember talking to the editor. This was published by Prentice Hall with Carl Karlstrom, the editor there. And I remember a discussion with him about how many copies do you think this will sell? And I had no idea. Well, maybe 5,000. So it's done better than that. Just as well.
That's interesting. That explains a lot on how do we get here, right? Also, its development began at Unix operating system for the PDP-11 computers. C has been implemented for practically all devices. Exactly, because you have now a program. Yeah, you have reading a tool that sharpens another tools and so on and so forth, right? Interesting. Interesting. So, having said that, so you have now and also the thing of not writing an operating systems at the assembly level is that on the assembly, which is very specific to that architecture, you want some kind of portability, man, here. Okay, so you want that your programs runs in any architecture. I don't care who you are, but run in any architecture. You know, you want your you want your contents to be ready available for boomers, Gen X, millennials, Gen Z, Alpha. I don't care. That everybody can get the message. Okay, and that's the idea of the C or the language C and the C compilers. And it makes a ton of sense. All of them are talking the same language, but these new generations of computers, they have their own lingua franca. Okay. And not only that, it all starts with this notion of the time sharing. Computers back in the 60s and the 70s, they were so big and so expensive. And you thought that your Mac is quite expensive? Well, that engineering, and he mentioned, for example, General Electric, they have these massive computers to organize their own systems, where now they want to allow developers to access to their research in this time sharing stuff, you know. It is of fundamental importance. So as I read here, it is of fundamental importance for many aspects of the computing and data processing. It serves as a lingua franca to translate between various systems and language. C is often used as a target language for compilers. Exactly. As an implementation language for interpreter. Interesting. Look at this, and this actually is going to solve a lot of these issues, or this question that I have here, is that how do Ruby or interpreter language store objects in memory here? So not only that C is often used as a target language for compiler, as an implementation language for interpreter, for building operating systems, for embedding programming, for teaching fundamental of computing, and for general purpose programming. It's a standard in terms of portability, interoperability, efficiency, and stability. So, all right, that was a great intro here. Now it makes a ton of sense why we are using here. So that'll be all for this video. Take care. Bye-bye.